So in the last class, we had barely touched upon this common source amplifier with source degeneration. Okay, so this is the circuit that I have, and what we found is that the gain expression could be expressed as capital GM times R out, and we also spoke about what is our capital GM, and it was GM RO divided by Rx. So I'll just write it as Rx. So the value of Rx is given as the impedance seen from the drain. So it would be like R0 plus Rs plus GM prime Rs R0. Yeah. So this was the formula that we had for the GM, and then R out is again, it's a parallel product of RD and Rx. Okay. So this is what we had. Now after this, what we did is that we went on for further simplification just to have an insight of this particular formula, just by taking out the lambda to be equal to 0 as well as the gamma to be equal to 0. When we do so, we ended up having something like a capital GM to be equal to, what was the capital GM that we ended up having after doing all this manipulation? Yeah, it was GM, yeah, I think it is 1 divided by, right? Yeah, 1 divided by 1 plus GM. Yeah, where 1 by GM corresponds to the impedance that I see over here, and that when I add with the resistance, the total impedance that I see from here would be then 1 by GM plus Rs, and that entire quantity, 1 upon this quantity, was turning out to be something like capital GM for us. Okay, so this is applicable only when I have this lambda is equal to 0 and gamma that is equal to 0. Otherwise, I might not be able to have this result. And we also had this R out. When I apply these conditions, the R out has become something like RD. Okay, and finally, what we said is that one could write the gain equation under this condition, that it is a product of drain resistance divided by the source resistance with a negative sign whenever we are dealing with inverting amplifier like CS amplifier. Okay, now this particular form could be used only when I have this kind of conditions. Okay, otherwise you cannot use this kind of result onto this. Okay, so please ensure that you have this kind of conditions in order to get this results. Clear? So that would be a very short form, and normally for 1 mark you can use those kind of techniques to get your answers. Okay. Any doubt in this particular form? No, right? Yeah. So let us move ahead and see a bit more insight into these formulas, and then get ourselves comfortable with the large signal phenomena. Okay. Now 1 by GM. So I just want to plot this capital GM over this Vn. Okay. Now what happens when the value of Vn is lesser than the value of Vt? What happens to the capital GM? Would there exist any current first of all? Yeah. So whenever there doesn't exist any current, then the GM obviously will be taken as 0. So there is no problem in it. So I have this to be at 0. But what happens after this? And we have to compare ourselves with without source degeneration. So for which I'll just take one more graph, and this graph is without source degeneration. I just put it as Rs. Okay, so this was our graph for a circuit where we didn't have any Rs. Yeah. Okay. Yeah. So now, in order to address this, what I do is, like, first I will just draw this graph, which we have already done it. So till this particular point it was at 0, and after then we had a direct relation, right? Because GM was equal to Kn dash W by L Vgs minus Vt, and the value of Vgs is equal to our V in itself. So we had what type of graph after this? It was a linear line, right? After that it went down, so we will not worry about it. So I will just talk about the region where I'm really interested in. Okay, so I'm going to assume that the transistor M1 is in saturation. In that particular region, I have this kind of graph. So now how will I plot this guy? That is with source degeneration. When Vn is small, we know that obviously the GM will also be small, right? So this will also be small. So when I have this as my small quantity, what happens when I read it as 1 by GM? Yeah, it will be large, okay? So I have a large quantity in addition with a small quantity. So what would happen is that effectively this 1 by GM would be the most predominant quantity over there. So due to which I would almost have the same similar relation that I had here, okay? Because the GM of this structure, the capital GM is nothing but my GM itself or minus of GM, okay? We'll not worry about the negative sign. But the point is that this GM is same as that of GM, okay? Even when you substitute the same thing, because I have a large value of 1 by GM, the capital GM of this particular formula turns out to be same as that of GM itself, okay? So due to which I'll again begin with this kind of relation. But what happens the moment the value of Vn keeps rising? When I move towards the right, the value of Vn is keep rising, right? So what happens after then? Yeah, both the quantities would play because 1 upon GM will also come into play and even the value of Rs will also come into play. But what if I'm going beyond a particular value of Vn? The 1 by GM, what would happen? Yeah, it becomes too small. So effectively, for a larger value of Vn, I will not have this particular term. But what will I have is this 1 upon Rs, and that limits my maximum value of capital GM. So it will not rise. So basically, what happens is that there is a maximum value, and this maximum value would be something like this. And due to this interplay between this 1 by GM and then Rs, so they begin with this kind of graph, but after then they try to bend and then they approach a particular constant line, okay? Now, is there any problem with this kind of graph when I didn't had any source degeneration? What is the inference that we got out of this graph? Yeah, so just because when my Vn is changing, my GM is also changing, and due to which the gain was also getting varied, right? That was the issue. But in this case, you could be able to see just for the initial values of Vn, the GM is dependent on my Vn, and that is a problem. But once I cross a particular value of Vn, what happens is that the GM tends to be constant, okay? So this degeneration effect comes into play, okay? So that is one of the difference that we have between the common source simple structure with the common source with source degen, okay? Yeah. So I also wanted to plot one more graph which you might not appreciate at this point in time, which is ID versus VGS, okay? So again this is without Rs and this is with Rs. Yeah, or Vn or VGS, okay, so whatever it is. I think I better take it as Vn here, and this was already equal to Vn itself. Okay. Rather than using this as VGS, I am using it as Vn, okay. The reason would be from the structure you can get it. So having this as my plot, let us first try to plot this first graph without Rs. So how does this graph would look for a current? Yeah, it's a parabola that we have already been discussing, right? So till VTH there is no current, and after then it goes something like a parabola, so it goes steeper like this. But when I try to plot the same for this, how would this graph? So initially I would have the same thing, there is no change in this plot. But after that, what happens to the value of current as I increase the value of this Vn? Huh? Yeah, in the similar way that I have here, or will there be any change in this current relation? You see, whatever the value of Vn that I have is actually falls across two components. One is across the VGS, the other one is it is getting dropped across my Rs. Okay, it is not as we had earlier. Whatever the value of Vn was directly applied only for our VGS, whereas in this case it is being split across two people. One is VGS, the other one is our Rs. So now what happens is that as you keep increasing the value of Vn, the drop across this will almost stays constant. Now why that? Yeah. Yeah, sure. Yeah, so whatever he said is that, you see, the point is that as I increase the value of this Vn, the VGS is also getting some value, and due to which some current is flowing. Now this current, when flows across this resistance, it creates a voltage here. So previously we had a voltage of 0, but as the current flows through this resistance, the drop across this resistance also rises up. So any change in Vn is actually being equally raised by the source terminal as well. Am I right? Yeah. So we have already discussed about this action. When I tap the output, rather than tapping the output from the drain, if I tap the output from the source, what type of action we are seeing? Not current, but some special name is there for us, for that. We discussed about it. Source, some source follower, right? We discussed about it, right? We had a discussion about the source follower earlier. So the point is that this particular node voltage will follow my input with some offset voltage. That depends on the current that flows here. Okay, that offset voltage is nothing but the VGS. So if my VGS is 1 volt for 1 milliampere of current, then if my Vin is at 2 volt, then this voltage would be at 1. And if I increase this guy, the input voltage to 3 volt, then obviously if I still have the same current of 1 milliamperes and for which I need a VGS of 1 volt, then this would be raised up to 2 volt. So you could able to see, apart from this offset, both these values are being raised up at the same time. Okay. Now if that is the case, how will I draw the current for us? Yeah, some sort of linear relation we have, right? This Vs I could approximate to a value of V in itself. Am I right? Because apart from the offset, my source voltage is following my gate potential. Okay, so it's almost equal. And in order to read out the current, what I do is that this, when I divide by the resistance, I would get the current. When I try to plot ID versus Vin, you would get some sort of straight line or a slope. Okay, and the value of this slope is actually equal to 1 by Rs. Okay. Now we will utilize this result later on, back when we discuss about the common drain amplifier. But as of now, the current that I had here was more of non-linear, whereas the current that I am having here for a source degeneration is more of linear. Okay. So now let us talk about the small signal voltage. Okay. A small signal voltage gain as a function of input voltage. Okay. So what I studied before was just GM versus Vin and ID versus Vin, but right now I really want to talk about the gain versus Vin itself. Okay, and I am just putting the modulus just because it's a inverting amplifier, so I want to read what is the positive value of the gain, due to which I am just substituting this modulus. Okay, now how will I plot this? Again, what are the concepts that we have learned just before? We can utilize those concepts onto this graph, especially on the GM that we have studied. We know that the gain is always a product of, okay, let me put, right, and what happens when we plotted this GM versus Vn, for higher values of Vn, what has happened to the capital GM? Yeah, it went on to a particular value of 1 by Rs. Okay, so what was our R out in that case? It was, yeah, it was approximated to a value of Rd. So the maximum value that I can get out of this gain would be just Rd divided by Rs, right? So that I can put it here, and the way that they react will be almost identical to what I have got it for the GM. Okay, so I think something like this till Vt no gain, and after then it goes something like this and settles down to this particular value. Okay, so again when I look for the gain is completely dependent on the factor between the drain resistance divided by the source resistance. Okay, and it doesn't depend on any Q point here. So again, it's a kind of advantage that we have. Clear? Yeah. Now let us go for a quick, and all of these things that I am talking is to a particular voltage of Vn that makes my transistors operate in saturation. Okay. So it is not valid for Vn that is beyond which my transistor is entering into linear. So I'm not discussed about any of these concepts in the linear region. Okay. So I've discussed only with respect to cutoff and saturation. Clear? So if we go beyond this, obviously the gain will drop. I'm not discussing any of these things here. Okay. Yeah. So let us do a simple problem, a quick problem. Assume that the gamma, lambda are all equal to 0, and then I just want you people to calculate the small signal gain. This is just a 1 mark answer, okay? So you should be in a position to quickly tell me the answer. It should not take even a minute. 4:15 right now. In 4:16 you have to tell me the answer. I have given that a few assumptions. Make use of that assumptions. Don't. Yeah. So I have just told that the gain, whenever I have this condition, I can always write the gain as something like drain resistance divided by the source resistance, right? And if it is an inverting amplifier, put a negative sign at the beginning. Okay. So that's it. So the only thing that I have here is that the drain resistance was RD, so I can just put RD here. And now that I need to find the source resistance. So what is the resistance that I have when I look through this M1 source? 1 by GM1. So when I look, sorry, not here. Yeah. 1 by GM in parallel, or how will I take this total resistance? Okay, I think probably if it is confusing you, I'll just redraw the structure by replacing this bottom transistor M2 as something like a resistor, okay? And this resistance value was 1 by GM2, okay? This is my M1 and RD I have, and this is my Vout. So, as I said, we already know that this impedance that I have when I look across the source is 1 by GM1, and after then I have 1 by GM2. So I have to sum both these quantities as the source resistance, okay? So these two has to be looked right from this point. Do not go below this, because that will make your answer completely different, okay? So don't do that. Look from this point of view, look up and down, and in this case it will get added up, okay? So don't put them in parallel, they are in series. So the total resistance, the total source resistance is a summation. So that would be like 1 by GM1 plus 1 by GM2 with a negative sign at it. Any doubt in this regard? If you have any silly doubts or confusion, you please ask me so that we will clarify that. Now, in order to build this common drain, like, where do I apply my input and where do I tap my output in the case of a common drain? The input has to be across the gate, but the output is taken from the source, okay? So now, then where do I fix my drain then? To the AC ground? Yeah, that is a better answer. So in short, it will be, if at all, if I'm going for an NMOS, then the drain will be connected to the capital VDD, and that when I translate to a small signal model, this drain would then translate as AC ground, right? So across the source, I have to tap my output. So whenever you want to tap an output, can the source could be connected to the ground? No, because this transistor will generate only the ID. But if at all, if I want a voltage, you have to pass through a load, okay? I've seen many people missing out this, directly tapping this as my output. That is not at all possible, okay? So you need to pass this current that you have generated from the transistor through a load. It could be a resistive load or it could be anything, okay? So let us take a resistive load and then we'll do it, okay? So this is known as a common drain amplifier, okay? Now this common drain also has a special name which you had just now, yeah, it's also called as a source follower, and we discussed more about it, so I will not go much in depth. So in general, this common drain configuration has two type of structures, one with resistive load, the other one is with the current source load, okay? Now shall we try to plot the relation of Vout versus Vin for this? Now how will I plot this? When I reach to the value of Vin, Vin that is equal to VDH, what is the value of voltage that I will have? 0, right? Because no current would flow. So there is no enough value of VGS here, due to which the capital ID would then goes to 0, and when no current is flowing, what is the voltage that I will have here? 0, okay? So any potential that I have here, that will be translated here, okay? So it will be 0. And after then, what is happening is that initially there will be a kind of small slope, but after then it will be a very straight line just because it's a source follower, okay? And this is the kind of straight line, not a line like this. Yeah. So this is how you get it. So now let us try to evaluate the gain of this particular circuit. And this circuit is basically the resistive variant of common drain, okay? And later we'll replace this RS with current source load. But as of now, I just want you to calculate the small signal gain. Yeah, so got the answer? So what was the gain, V out by Vin? First of all, is it a inverting or non-inverting? Non-inverting. You should get a positive value of GM, okay? Now, did you get the value of GM? What we do when I try to compute the capital GM, I short the output node to the ground. So when I do so, nothing would go through this RS, okay? So this will not be there. But what current is flowing here? It is the ID. So what is this ID? How is it related to Vn? GM times that of VGS, right? So the capital GM would be exactly equal to GM1 itself, if at all, if this is M1, okay, no change. The only thing is that it is no more a negative quantity, but rather it's a positive quantity. Clear? Yeah. So what about the R out? So again, when I look down, I'm looking as a RS value, okay? When I look upward, I have 1 by GM1 parallel with RO1, and if you want body effect, we can just put a prime here, and then everything goes in parallel with RS. Okay. So you just multiply both these quantities to get the answer of gain. But rather than going like this, I just now spoke about the impedance seen from the source terminal. Am I right? So I'll use that concept to build this expression over here. Yeah, so what I know is that whatever the impedance that I'm seeing towards the source is nothing but 1 by GM in parallel with GMB in parallel with R naught, okay? So when I translate this in terms of small signal, the drain is connected to my ground, so I connect that, but the gate is connected to my Vin, so I substitute the small signal Vin here, and then the source end is connected to RS, and this is my V out, okay? Now, how will I map these resistance value, all these three resistance value? So again, what I have is that 1 by GM is always falls between the gate and the source, so I put that here, and 1 by GMB falls between the gate and the body, sorry, between the source and the body. Since the body is already at the ground, I just put as 1 by GMB. And then what about R naught? It falls only between source and the drain, right? So I just put that as well as R naught, okay? So now what type of circuit is this? You see that RS, 1 by GM and R naught, how are they connected to the source? They are in parallel. So I have a simple voltage division between V out and Vin, right? So this circuit has something like this, where I'm reading at this point V out, and at the input I'm feeding my input Vin. So the value of this is something like this, right? So yeah, so now that when I try to manipulate this, the V out is nothing but Vn into this term, which is 1 by GM in parallel with RS, divided by 1 by GM okay. So just manipulate this, you end up having the same result. So here is a plot of gain versus Vin. How would we plot this graph? So the maximum gain out of the circuit is 1. Why is that? it's a source follower. Okay, so just because it's a source follower, I would have a maximum gain of 1, but ultimately will be still lesser than the value of 1 just because of the eta factor. Okay, so I think my time is running up, so yeah. So calculate the gain of the circuit by making use of this voltage divider method that I've just spoke about. So got the answer for this? I think it's a pretty simple. The only thing that we have is in the place of RS, I have R naught. Okay, so everything else remains the same. So in the next class, we'll begin with this common gate, and I somehow have to complete fast. So maybe I'll try to upload the video, and then I will like Tuesday you have to watch the video and then come. Okay, so please intimate to your friends as well.